So this example that I want to look at is going to be looking at the relationship between carbon stored in the soil and the depth of the measurements that we take. So we've kind of covered this a little bit in some of the other material that we've looked at, where we've seen that soil carbon storage is a really important part to play in the whole carbon management cycle. So in this case, we've got some CSIRO map here that's showing you some information on the way or the amount of carbon stored in our soils. The setup that we're going to have is we're going to have two measurements. So we're going to have a measurement of a depth, and we're going to have a measurement on the carbon content of the soil. So I'm not looking at two groups. I'm not looking at two different depth levels. I'm looking at continuous measurements of depth. So I want to be describing the average change through time as we move to greater depths. So the dependent variable is the soil carbon value. So I'm saying that the thing that's doing the explaining is the depth. Okay, so sometimes it's not always intuitive in how we present this, but in this case, I think it makes sense to say, look, the carbon value that we get can be explained by the depth that we're sampling. So that's why I think that the dependent variable should be soil carbon and the explanatory variable should be the depth of the measurement. Okay, so what do we want to do? We want to look at the data first. So that's important because there's often mistakes happen when we read in the data. So let's have a look at this. There are two ways to look at the structure of the data. We can use the structure function. You can see that it says I've got two variables. I've got depth and I've got soil carbon content. And I've got 8 observations. I can also use the summary, and it gives me the 5-number summary. So the 5-number summary, remember, is what a box plot gives us, and plus the mean. So we've got 6 values there, and I can see, okay, so my depth measurements are going from 1 to 200, and I can see my soil carbon measurements. So what do we want to do? Because we want to understand the information and we want to present it in a way that other people can understand, we're going to plot the data. So we start off by just plotting it with the raw data, just applying the plot function. So this is what we get. Okay, and you can see here that it's got this exponential decay pattern that we might be familiar with from looking at a whole range of things. So when we looked at pollution, this was the same sort of pattern that we get. It's exponential decay. Actually, if I start to think about this, and I'm trying to think about how through this, you can see I want to make this a line, and you can see that, well, what do I want to do? If I was to squeeze up the values on the x-axis, then I would be moving more towards a line rather than a curve. So we know that we can squeeze up the values with the log transformation. So there we go. You know, we can start to actually think through these. It's fine to just run through all of the plots, but when we think about what shape it is, then that gives us some understanding of what kind of transformation that we want to do. So I'm going to say, look, we think that we've got some intuition from, you know, what's going to work, but let's just run through all of the options anyway. I can plot the raw data, which we've just seen. I can put the log transformations on either the X or the Y or both. Okay, so saying things about this, it's not going to be perfect. Part of the skill you need to develop is to exercise some judgment. So let's have a look. So when I put the log transformation on the X-axis, it does what I thought it would do. It squeezes the values up, and then in squeezing them up, it starts to look like I have something that is approximately linear. It's definitely not perfect, but we're not looking for perfection. We're looking for the best possible representation we can come up with. This one I've gone for the log on the Y, and it's actually done something that's not too bad. I just think that it curves away at the bottom a bit there, and I do get these values all bunched up at the top. And remember, we're looking, when we thought about how to explain fitting our line, if we have more spread in the data, that makes it easier to fit the line. So I'm not really that happy with this presentation. And then if I apply the log, well, yeah, this just doesn't look good at all. So I pretty much can rule out the log, and I actually think that of all of them, the log on the x-axis was the one that worked the best. Okay, so it's a matter of judgment, no right or wrong here, but there are definitely, I mean, I would think that you could clearly rule this one out. You might be, I don't think that this is great, but you know, you could make some argument about this one. And I think that this one looks better. So if I'm looking at this and this, I think that this looks better. I think that that definitely doesn't look good, and I think the original definitely doesn't look good. So, you know, you can rule some out as clearly not being applicable, but exactly which one is the right one is sometimes, in fact, in many occasions, not clear. So what are our next steps? We're going to create a plot. So we've decided that I'm going to have the log transformation on the x. That's going to be the transformation I apply. I'm going to fit my model so I can add a trend line. I'm then going to conduct a test of whether the slope is statistically different from 0. So whether it could be just due to chance that I got this estimate, or whether it's truly a true slope. And I'm going to report on some model fit metrics. Okay, so how do we estimate the model? I'm just going to save it as LM1. So it's carbon explained by the log of depth. I'm then going to draw my plot. I'm going to add my plot. I'm going to control my plot. So instead of having the default PCH is for point change. So I'm using 19. 19 is a solid dot. It's a small solid dot. I'm going to add my line. So I use the AB line to get the intercept and the slope coefficient from my LM1 model. The color of my line I want to apply is gray. So remember that AB is standing for A is for intercept, B is for slope. In our model, we write that as alpha and beta. And then my legend. So I want to put my legend in the top or somewhere. Okay, it could be here. I've just put some example here. Bottom left. I think I actually plot it in the top right. We'll see in a moment. The legend, they're the words that are going to appear in your legend. LTY, that's line type. So 1 for a solid line, there's nothing. So the solid line is going to match the trend. The point change, NA, there's no points for the trend line. There's only points for the observation. So that's why you can see the line. You need one line to match the word trend and dots to match the word observation. Colors, black and gray. BTY is whether or not to draw a box around your legend. Often it looks better if you suppress that. So I put no. Again, there's lots of examples for you to follow. So that's the code. What does it look like? Okay, so there's my plot. And in fact, you can see there I did put it in the top right. I've got log of depth, fitted my trend line. You can see that it's a reasonably good description. Formally, in writing up our results, we have a results table which describes the slope coefficient, and it also gives the measure of whether or not it was statistically different from 0. So we've seen that. That's how we apply our t-test to the slope, and all of that is reported in the summary values when we apply the summary. So here's my model here. So if we can see here, I've got summary. I've applied the summary function to my linear model, lm.soil, and I get the coefficients. So the coefficients is the bit that we want to look at. So you can see there's my log of depth, and it has conducted a t-test. The t-value is -16. We know from looking at t-tests that once we get beyond an absolute value of 2, it's going to be statistically significant. That's what it's reporting over here. So it says, here's my estimate standard error. I use the estimate to get the t-value. So we take the estimate -0. So we test out whether it's different. We're testing whether the slope is different from 0. So it's the estimate value -0.078 minus 0, because that's the null, divided by the standard error, which is 0.0041, gives us our our calculated t-value, which is 16.8. And we know from the p-value that 16.8 is far from 0. So because this guy here is less than 0.05, we conclude that the slope is statistically different from 0. Okay, so we're going to use that notation to put in our table. We're also being aware of this r squared value, so reported as multiple r squared in r, but we just say r squared, 97.9. So this says we can explain 97.9% of the variation in the data from our model. Okay, what about interpretation? Okay, so we would divide through by 100 because we put the log on, and we would say 1% increase in soil depth on average results in a decrease in soil carbon of 0.0008 units. So these are measurements in tons. So if you had all those, you can imagine that would be fine. You could just report this 0.0008 tons, but you also might want to switch it to kilograms. So that's sort of, a finer level of thought. So, well, is tons, when I'm reporting 0.008, is that the best metric? Or maybe I could convert it to kilograms. Similarly, if you had, very large kilograms value, you might say, well, should I convert it to tons? But it's okay at this stage to just be working on the raw scale. Our R squared, the 97.9% of the variation explained. Our summary table, how do we report this? So this is the central thing that we need to be aware of. We're going to take the summary that R reports and we're going to collate a summary table. So we're just going to use a subset of the information. Key things here, here's my estimate of the intercept. The p-value was less than 0.01, so we're going to denote that with 3 stars. And we're going to report the standard error values, the R squared and X. And this is something that we do in regression, which we haven't really been doing in ANOVA. It turns out that the convention is, instead of just saying alpha is 0.05, we're going to say, well, some people might be really interested in an alpha of 0.01. Some people might like 0.05, some people might like 0.1. So we're giving this flexibility. We're going to say, you as the reader could have a preference for alpha of any of these 3 values. We're not going to tie you to just saying 0.05. I mean, this tends to be the convention, but some people like more evidence. Some people are willing to accept less evidence. So we put stars, we report the standard errors, and we'll put 3 stars if the p-value is less than 0.01. We put 2 stars if the p-value is less than 0.05, and we put 1 star if the p-value is less than 0.1. Okay, so we need to get our star system in. In fact, most of the examples we work with will find where the p-value is actually less than 0.01. So we're often putting 3 stars. But this is an extra level of flexibility. So that's the final sort of nuance. Instead of just saying alpha is 0.05, which is probably the one that we most work with, we're going to say, well, you could have some different levels of alpha. And we're going to give you some indication of statistically different at different levels of alpha. And that's what we convey in our summary table. So this is the way that we write up our results. This is the style guide, so a double line at the top, single line here, and to separate this different level of information, the information on the intercept and the slope, from our model fit information, which is how many observations we have, and the R squared value, we use a dashed line. And that's an opportune time for a break.